everybody. So in the last one, we had developed the first derivative test. So first, let me just remind you briefly what that is. The first derivative test, I'll boil it down without as many details. We look at critical points, and our critical points are our critical numbers. If the first derivative changes sign, then we have a max or a min. And if the first derivative doesn't change sign, I'll just put no change, then we have no max or min. Right? And then we can break down this first part even further, that if the first derivative goes from positive to negative, we're looking at a max. And if the first derivative goes from negative to positive, we're looking at a min, right? And this just gets into how the derivative tells us about the shape of a graph. And in particular, we're looking at the derivative tells us whether the graph is increasing or increasing, okay? Now, this has to do with places where the function is continuous at the critical number and nearby. And so these two examples here, the max and the min, if we have a positive derivative, it means our function's increasing. And then at our critical number, the derivative is either zero or doesn't exist. And then after the critical number, our function decreases, right? That's the derivative going positive to negative. And we see that we get a maximum, a local maximum. And then if the derivative is negative, we're decreasing. And then we increase after the critical number. So we get a local minimum, right? So that's what that's the picture of those. So we had looked at a certain function that I want to dig a little more deeply into. We had looked at h of x is equal to 2x squared over x squared minus 1. We found its derivative to be equal to negative 4x over x squared minus 1 squared. And we took a look at the sign. So we found critical numbers. Let's say that first. Critical numbers at -1, 0, and 1 at these x values, right? So this is all in the previous video. And what we did with these critical numbers, so at the critical numbers -1 and 1, the derivative doesn't exist. So we couldn't really use the first derivative test there anyhow. But we did find that at the critical number 0, we had a local maximum. The way we did this is we looked at the value of the first derivative in these 4 regions of the real number line, right? So if x values were less than -1, we found that the derivative was positive. If between -1 and 0, it was positive, and then between 0 and 1 is negative, and bigger than 1, it was negative, right? And so that's how we identified this maximum, where we see that the derivative went from positive to negative, right? But now I want to look at something else. Notice in the region below -1, our derivative is positive, and it's always positive. Between -1 and 0, it's positive. And then it's negative and negative in the other 2 regions. That means in each of those regions, in each of the positive regions, the function is increasing. And in each of the negative regions, the function is decreasing. So I want to look more closely at these regions of increasing and decreasing. Why don't I put in the 2 asymptotes. Let's make this a little nicer though. How about black and dotted and maybe a little thinner. Okay, so there are our 2 asymptotes, okay? Those were where 2 of the critical numbers were, and then the third critical number was at 0, was that local maximum we found. Now, what I want to look at is, we're going to start at the region below -1. So this left third of the screen, more or less, to the left of -1, where we've got the function approaching that asymptote, shooting off to infinity. The function's increasing there, which is what we had just said it would be doing. But I want to look at a little bit at how it's increasing by looking at the tangent lines. So that dotted red line that just appeared is the tangent line at x equals -6. I'm gonna scroll the tangent line closer to -1, and I want us to look carefully at what's happening to the tangent line. Turn that thing off. The tangent line is increasing its slope, right? It's always a positive slope. It's hard to tell here, but slightly increasing. And as I move to the right, let's put in the point A, h of A. As I move to the right, we can see that the slope is getting larger, right? Here, we have a very, very steep, very positive slope. So the function is not only increasing, the slopes of the tangent lines are getting higher the whole time. If those slopes of the tangent line are telling us how the rate of change is moving, increasing tells us it's positive, but bigger positive numbers tell us it's increasing even more, right? So if we look, for instance, at this region of the graph, let's look at right, somewhere like here. If I increase my input by ½ a unit, right? I went from -3.5 to -3. I can't even draw how small this changes, right? The output barely changes. But if I look over here, if I increase my input from -2 to -1.5, we start to see a more substantial change in the output. And then if I increase just a little bit after here, I can't even increase a whole ½ a unit because I hit that asymptote. But if I only make it part of the way there, the change is quite substantial, right? We get this huge jump, and those jumps are just getting bigger and bigger. In other words, it's not only increasing, the way in which it's increasing is increasing. It's increasing more each time we move to the right, okay? Let's hold that thought for a second. Now, I'm going to continue to move these tangent lines to the right. Right, it disappears there. Whoops, for a second. It disappears. That's when I put in A equals -1, where the function's not defined. And then we start getting tangent lines on that bottom part of the graph. Now we're on the right side of that asymptote. We're between -1 and 0. My function is still increasing, right? But it's increasing in a different way. Now, the slopes of the tangent line are getting smaller. They're still positive. We're increasing, but they're getting less positive, right? By the time we make it to the top, that tangent line is horizontal, it's 0. So here, right, if we're gonna estimate this tangent line, looks like it's got a slope of about 10. It goes in ½ a unit, it goes up about 5 units, right? It looks like it's about bigger, somewhere a little bigger than 10. By the time I move here, it looks like we're maybe a slope of 1, something like that, right? So it's a much smaller positive number in a pretty short amount of time. And then when we get here, it's 0. So both sections of this graph, between -infinity and 1, we have an increasing function. And between -1 and 0, we have an increasing function. But they're increasing in different ways. The one to the left of -1 is increasing how much it's increasing, and the smaller section between -1 and 0 is decreasing how it's increasing, which is a little bit strange to think about, right? But it's not that hard to think about. It's equivalent to, if we think about being in a car, 2 cars can be moving forward, and all it means is one is speeding up. The way in which it's changing is increasing. It's increasing its distance, and it's increasing how it's increasing its distance. Where another car can be moving forward and slowing down, right? That's a good way to think about this. They're both moving forward, but one's speeding up and one's slowing down. Similar thing can happen on the negative side. Here, where the function's decreasing, now this is a very slightly negative sloped line, right? You can look at this line and see it's very shallow, but as I move close to that asymptote, it's incredibly negative now, right? So it's gotten much more negative as we as we move. So the slope is decreasing, getting more negative, going down the number line. But as we get over here, past to the right of the asymptote, now it starts out incredibly negative, right? It's almost straight up. It's a huge negative slope. And it's getting more closer and closer to the positive numbers, right? It doesn't get there, but it gets flatter. It's getting closer to zero. So it's also increasing. So now we've seen there's a lot of increasing and decreasing to think about. Functions can be increasing or decreasing, and they can be increasing how much they're increasing or decreasing how much they're increasing. And a function that's decreasing can be increasing how much it's decreasing or decreasing how much it's decreasing, right? Same metaphor as before for the decreasing. It's a car going backwards. It's decreasing its position, and you can be speeding up, moving backwards, or slowing down, moving backwards, okay? It's a bit complicated to think about, but it's we'll keep working at it, right? This concept, right, you can see in this graph, there are certain shapes associated with this. So let me say more clearly what I mean. Let me get rid of a couple of things here. Too much going on, I think, for now. Notice this region to the left of -1, right? We've got a curve like this, or at least a piece of this curve. We've got the same kind of curve over here. In between, we've got a curve like this. Okay, now remember what we said in this region, the slope was increasing. In this region, the slope was decreasing. And in this region, the slope was increasing. And let me be clear, this is the slope. The function itself, for instance, in this region on the right, the function is increasing. But the slope is also increasing. Here we have an increasing function and an increasing slope. But here I have an increasing function on the left, and here I have a decreasing function. So we see that we can have any combination, regardless of whether the function's increasing or decreasing, we can have the slope doing the opposite or the same, it doesn't matter, right? So when we have an increasing slope, we always have this kind of, you can think of it as part of a cup or a bowl, right, facing upward. We call this concave up, that shape, right, or part of that shape, right? This section here, right, is like, it's like half of this. It's this half curving up here, and this is the same thing, right? This one's concave up as well. And then we call this shape that looks like a hill concave, or an overturned cup concave down. Okay. So let's summarize a little bit what I just said. Let's write this all out. Let's get a new page. Oops, turn this off. All right, so this new concept of concavity only tells us, it doesn't tell us whether the function itself is increasing. It tells us what's happening to the slope of the function. If the slope, and I shouldn't say the slope of the function, the slope of the tangent lines of the functions increasing, we call this concave up. And it's a shape like this. If the slope of the tangent lines are decreasing, it's concave down. And our shape is like this. Now, what does it mean if the slopes of the tangent lines are increasing? What tells us about the tangent lines? The derivative does. So the slopes of the tangent lines increasing mean f prime of x is increasing. And being concave down means f prime of x is decreasing, right? So if the slopes of the tangent lines are getting larger in that region, it must mean that the derivative is getting larger because it tells us the slopes. And if they're getting smaller, then if the slopes of the tangent lines are decreasing, f prime must be decreasing because it tells us the slopes of the tangent line. Well, we know from the previous sections that we can tell if a function is increasing or decreasing by looking at its derivative. If the derivative is positive, a function is increasing. If the derivative is negative, a function is decreasing. The derivative of f prime is f double prime. So if f prime is increasing, f double prime must be positive. The second derivative must be positive. And if f prime is decreasing, f double prime must be negative. Okay, so we can now, we're getting more information about the shape of a graph from the second derivative, because it tells us not only whether it's going up or down, but how it's going up, right? So you can be increasing and concave up. Looks like this. Increasing, functions increasing, and we're concave up. You can be increasing and concave down. Looks like this. Increasing, concave down. You can be decreasing and concave up. Or you can be decreasing and concave down. Right, so notice the concave down graphs are part of a shape like this. The concave up graphs are part of the shape like this. Which part of that they're in depends on whether they're increasing or decreasing, right? So it gets complicated. We've got our function, we've got the function's derivative, we've got the derivative of the derivative, the second derivative of the function, and we want to be able to keep all of them straight. And we're going to do more examples to help with this. But there's a big point we can make with this. If we look at let's do a sketch. Actually, let's start a new picture. If we have a function, let's look at this point here. Let's call this point. So this is our function f of x. Let's call this point c f of c. And let's say c is a critical point. C is a critical point of f, right? And for simplicity, let's just say that it's the kind of critical point, because of the way I've drawn it, looks like the derivative is equal to 0 at that point, right? And if we conducted the first derivative test, we can probably see by looking at this that to the left of, let's write this, the first derivative test, to the left of the number c, below c, you can imagine pretty easily the slopes of the tangent lines are negative. So if x is less than c, near c, right? So nearby there, it looks like f prime of x is negative. And then if x is greater than c, but still near c, it looks like the derivative is positive, right? So I'm just imagining what tangent lines might look like. To the left, they're sloping down. To the right, it looks like they're sloping up, okay, nearby at least. So what we've seen is that our derivative went from negative to positive as we passed through the critical point, which from the first derivative test tells us that it's a local minimum, right? That's what that first derivative test told us. But if we're going from negative to positive slopes, it must mean that our slopes, the slopes of the tangent line, are increasing, which we just decided meant the second derivative is positive, which means we're concave up, right? And that also tells us that we are looking at a local minimum. This is an alternative way to determine that, because if we're concave up, our derivatives have to be if we're concave up, the derivative has to be increasing. And so as long as we're differentiable at the point C, as we pass from left to right, if we're concave up at C, our critical number, it has to be 0, and it's increasing, it must go from negative to positive. So concave up at a critical point that also is differentiable, meaning its derivative must be 0. If we have this, it implies we have a minimum. And if it's concave down, we'll have a maximum, right? There's what concave down looks like. There's a critical point with a slope of 0. And so we have to have a local maximum there. And this is what we call the second derivative test. Okay. It's an alternative way. It's an alternative way to test for maximums and minimums at critical numbers. All right, so let's state this test. It is that if f prime of C equals 0 and f is continuous over an interval containing C, then if f double prime of x is greater than 0, we're concave up, then C is the location of a local minimum. If the second derivative is less than 0, C is a local maximum. And if f double prime of x is equal to 0, the test is inconclusive and you have to do something else. It could be neither, or it could still be one of them. You have to do some other kind of test, right? So let's see a quick example of that. Let's look at the function f of x equals x cubed. If we look at the first derivative, we get 3x squared. And it's easy enough to see that f prime of 0 is equal to 0. So that's our only critical number, is at 0. And f double prime of x, which is 6x, has the value of 0 at 0 as well, right? This would be in the range of this inconclusive test. So if we look at the graph of x cubed, I can sketch it really quick. The graph looks something like this. It has a horizontal tangent line right at 0, that 0 derivative. But notice it's concave down over here, and it's concave up over here, right? That's concave down, concave up, it's pieces of that. And it doesn't have a max or a min over here. It switches, in fact, right there from concave up to concave down. And so there's an example of an inconclusive test. This kind of point, by the way, where we switch from concave up to concave down, we call an inflection point. Inflection point. It's a point where our function is continuous and exists, and the second derivative is zero there and goes from positive to negative or negative to positive, anywhere where the concavity changes. Okay, let's do one last thing before we go. Let's look at concavity of that function we were looking at earlier, h of x, which was equal to 2x squared over x squared minus 1. H prime of x was negative 4x over x squared minus 1 squared. And then the second derivative, I'll spare you the algebra, the calculus work to get to this, was 12x squared plus 4 over x squared minus 1 cubed. Okay, let's think about concavity for this function. First of all, notice, so when we think about concavity, we're thinking about the second derivative. So we're focusing on this, the h double prime. The numerator, 12x squared plus 4, is always positive, right? You have the squared number is positive times 12 is positive plus 4 is positive. That's always going to be positive. So we really only need to think about the denominator to think about when it's negative. Well, what's going on in the denominator? We have a cube, so whatever the sign of the inside is, the cube will be that. If the inside of x squared minus 1 is negative, x squared minus 1 cubed will be negative. If it's positive, when you cube it, it'll be positive. So we really just need to figure out the sign of x squared minus 1. Well, when is x squared minus 1 positive? X squared minus 1 is positive if x squared is greater than 1, which happens when x is less than negative 1 or x is greater than 1. And then x squared minus 1 is negative if x squared is less than 1, which means x is between negative 1 and 1. Another way you can say this is, here we have the absolute value of x is greater than 1. Here we have the absolute value of x is less than 1, right? Because we're squaring this thing, so whether it's negative or positive, it becomes positive. And so having a value bigger than 1, an absolute value bigger than 1, means when you square it, you'll be bigger than 1. So negative 2 squared will be positive 4. Similar here. You can also think of x squared minus 1 as a parabola. Its two roots are negative 1, 0, and 1, 0. Between the two roots, it's negative. Outside the two roots, it's positive. Okay, so that's another way to look at this. But for our function, what this means is h double prime of x is greater than 0 for the interval negative infinity to 1 to negative 1 and union with 1 to infinity. And h double prime of x is less than 0 between negative 1 and 1. So here it's concave up. Here it's concave down. All right, we'll look at the graph in just a second. I'm also going to remind us we had a critical point, h prime of 0 equals 0, or the derivative of 0 at 0. This is in this region between negative 1 and 1, and it's concave down there, which predicts by the second derivative test a local maximum, right? Which is what we found before with the first derivative test. And so they both should always agree, right, if we're doing things correctly. And sometimes it's easier to do one or the other. So let's finish by going back to that graph, noticing that, remember we said when we're outside of negative 1 to 1, we're concave up, which is what we see in our picture here. And between negative 1 and 1, we see this concave down with this local maximum right at 0. Okay, that's it for this one. We'll do some examples in other videos of both the first and second derivative tests. They can be quite confusing at first, trying to keep track of all these different derivatives, but we'll take our time and work through it and sort it out. Thanks, everybody. I will see you next time.